Good evening. We're Team Overcooked. My name is Nick Johnson.
David Dockins.
Aekchanin, Iamborisut.
And Tyler Kidwell. And we developed the temperature monitoring and control griddle. This is our final product presentation, going over everything we've done. And our client is Dr. Aekchanin. All right, so our problem statement. So the main issue we're trying to solve here is that conventional electric griddles utilize what you can see right there, which is the very simple single probe analog dial temperature control system, which is going to cause temperature distribution issues, calibration issues, and through the use of digital user inputs and feedback and other display technologies, we basically made it so that the temperature control system distributes heat better and there's a better user input. So yeah, what we noticed with baseline testing is that there was a lot of overheating and large temperature swings. And we tried to fix that using digital feedback. All right, so this is our product overview. We utilized multiple point temperature feedbacks that we'll talk about in Module 3 using 9 different thermocouples on the bottom of the griddle. Obviously, like I said, we have digital user input and a display instead of just the analog dial, like is common for electric griddles. Everything's wall powered, and at max heating, it's about 1,500 watts. And the total budget was $497 plus 25% overhead takes us to about $600. So we stayed well under that $1,000 senior design budget. Okay. And this is what our final product looks like. This is the inside of it, obviously. You have the griddle on top that's opened up so you can see everything on the inside. There are the different modules there, and then on the outside you can see the user interface module. And then to the right you can see the before thermal pattern. That was for a different griddle with a different coil. That utilized the simple rheostat, dial, and on and off switching for temperature control, whereas the one at the top right utilizes our digital feedback with 9 sensors and a phase angle control module to regulate the power input to the coil. All right, Dockins.
So for the pretty face of our griddle, we have the user interface. Instead of turning a knob, you now use your keypad. And with the LCD screen, it lets you view your current temperature that you currently have, so you can monitor that temperature, as well as an input temperature. So you can input, say, 250 degrees, press enter, which is going to be your C, and that'll input that temperature. The LED matrix symbolizes where each sensor is located on our griddle, so 1 through 9, and it will turn green within a 15-degree error margin. That clear button right there is used to stop the thermocouple loop so that the user may input a new input temperature. So as I said before, our LCD screen displays input temperature and current temperature. You actively monitor the current temperature, so you can actually watch our griddle heat up and rise to stable out. And our input temperature is whatever the user's desired temperature is. Yep. For our keypad, we did a 9x9 keypad. For our inputs, we have 0 through 9. C is your enter button. D is your delete button. Say you enter 65. I don't want to put 65 in. Press D. Deletes it. How it works is I set it so you can only press the button of a max of 3 inside of that input. After 3, you can't put any more button presses into it, so you can't put 1,000 degrees into it. When you press delete, it gets rid of you pressing the button 3 times. If it's a valid input, so within 200 to 500 degrees, it'll say input accepted. It takes that numbers that are put into the string, makes it into an integer, and sends it off to a summers module, which then regulates and rises temperature. And if it's with above or below that 200 to 500 degrees, it will prompt invalid input, take 200 to 500 degrees. That's graphics module. And as I said before, these are LEDs. So they are defaulted to red, which means, it's not within that temperature. But once it reaches that 15 degrees, as you can see, the LEDs will start to turn green, while the ones that are still not within that 15 degrees will stay red. Yep.
Okay, so under the user interface, this is the inside of the griddle, everything we added to the existing griddle that we bought and modified from the original temperature control dial. So like you can see, we have a phase angle control module with a huge heatsink capable of taking high current. The Arduino Mega is what we use to control everything digitally. And then we have some power regulation for the small electronics. And then obviously, in and out of the phase angle control module is going to be 120 volts from the wall to heat up the coil. And as you can see on the left, that's what a phase angle control waveform looks like. It basically chops off parts of 120 volts AC from the wall to change the RMS value to the coil. Alright, so the control module. This varies, like I just said, the RMS value of the wall voltage into the coil from 0 to 120, given a PWM signal to it, and it provides interrupts to the Arduino so it knows when to actually fire and control that triac that's attached to the heatsink in the phase angle control module. So it obviously it supplies all the current to the coil. It's about 12 amps max when you're going up. When you first input a temperature and you're going up to max temp and approaching the user desired temp. And it evaluates the average temperature and sends signals to the phase angle control. Obviously, that all comes from the Arduino. And then the phase angle control module has a fan powered by the power regulation part of this module.
And this is a brief breakdown of our power supply. As he stated before, that we have the regulators to do 12 volts and 5 volts to power our Arduino and other applications. Primarily what we have here is, of course, the 120 volts coming straight from the wall. And we had a picture earlier to represent the old sensors that they used with the dial, usual stuff in there, and just the one temperature sensor. So what we did was we ended up cutting out that big problem, using the same idea just so you can have the ease of use to be able to plug it into a wall and be able to use it. That will take that input of the AC input, break it down into DC, and that would come over here to help regulate it so it wouldn't burn out any of our other components. And of course, what it's actually going for is the amplifiers, the PAC fan, some other circuits that we discussed with the LCDs and the keypad.
For temperature sensors networks, we're using 9 thermocouples, and we decided we have to use 2 amplifiers. So this is the pin diagram connected to Arduino, and that picture is the actual thing that under the griddle. Yes, and this is like the flow chart, like for the sensor. Since it has a multiplexer, we have to select multiplexer and then read all of it, 1 to 8, and then another one, from another amplifiers, and then send it back to the LED and LCD screen and Johnson model, like the power. And this is how we connect it to the under the griddle. We have to use sodium silicate to separate the wire. Like if it's touching each other, it shorts the circuit, and it cannot read anything. So we have to use this to separate it from the griddle, but still transfer the heat to the thermocouples.
And these are our obstacles. The very first one that we ran into in the beginning was originally we had 4 modules, and one of those was to redesign our coil and to try and be able to manage the heat and spread that out evenly and as efficiently as we possibly could, but that took a lot, so we ended up scratching that, hence why we got a new coil design from this other griddle. We also had to work out the thermocouples. They still kind of get those error values, I'm sure as you guys saw through the walkthrough, where sometimes once it did hit that value, it might just go all red. but we ended up being able to negate that and still being able to read a reasonable temperature. Our control module, at first, we had to go through a few different areas to be able to find out which one would actually be able to handle the 120 volts coming out and the powers that we actually needed to supply the griddle and the rest of the circuits. And then the material that we had to use for the thermocouples, originally we had these isolating panels, tiles, something like that. Yeah, those insulators, but they were shaped like a square. They weren't very good at that. Plus they had like asbestos in them, I'm pretty sure. We cut out to them. But we're used to that, we're in this building. Asbestos-like, sorry. And then we had to figure out the proper spacing for the sensors underneath to be able to get more accurate and, again, more efficient readings.
Alright, and another thing is the amplifiers. So like, I connected to the like plus and minus, and then it's reading earlier like backwards. So I have to flip it around. Like the board is.
All right, our product achievements. It is actually a functional product. It is actually a functional product. Like if you walked around, you would see that really the only issue was that sometimes we get bad values from the thermocouples, which we still have not completely been able to eliminate yet in terms of the LED display. Like you can see it sometimes went red when it got bad values, but other than that, it works mostly to the objectives we originally set at the beginning of the semester, which are there on the right. So obviously cost below 1,000, be able to regulate the input versus actual within 3 degrees. So if you saw the top and the bottom temperatures, they'd stay within 3. Incorporate digital user input, so module 1. Sample the cooking surface with 9 temperature sensors. The 90% part we didn't quite meet. The idea behind that was to cover the surface about 90% with the adhesive, which is highly thermally conductive. That wasn't quite covered 90%, so that one's in yellow. And then evenly distributed cooking surface having no more than plus minus 15 variations. Even when it hits that settling points, some of the LEDs will go red, meaning that it is outside of the plus minus 15, so that's not quite met. But a lot of that's mechanical engineering stuff that you just can't, even with feedback, get those far points to be the same temperature as the middle points. There's nothing you can do. But we did improve it a lot. The other thing, so yeah, objectives met, it's a complete product, it's all in a casing, it looks like a product, you can port, or it's portable, it's safe, gets everything from the wall. There's lots of unique features, my favorite being the LED display indicating the temperatures of the surface. So yeah, all that, I thought was pretty successful in the end.
Look out for the pancake cooking video tomorrow.
All right, any questions?
Did y'all try it with, like, actually try to cook something? I didn't know if you've already done the video, but.
We cooked water on it. And it seemed like when we poured the water on it, the LED would turn red where we poured the water, but then it would rise back up. So.
We spilled some chemicals on the surface, so we didn't want to put anything on it. We gotta clean it really well.
Yeah.
I still decided to put food.
Food was still put on there.
Science.
Yes, sir.
So this is obviously a consumer product, so there's all sorts of regulations and things governing that. Can you address some of the safety things that you have to take into consideration because it's something that people would be eating off of and cooking with and possibly spilling pancake batter down into the...
Yes, sir. Okay, so I guess I'll address like the high voltage safety part of it. Maybe y'all can address like the food and spill and stuff. But there are obviously standards for using high voltage and having metal casings for like kitchen appliances, you know, and such. Obviously ours is a 3D print case, so there's no issues there. It derives all the power from the outlet, but all the wires are contained under the surface of the griddle. And 120 volts is completely isolated from any metal, obviously because the case is 3D print. We have AC/DC converter for all the other power electronics which go to the user interface which you'd be interacting with. So there's high voltage safety we considered.
With along the lines of like spilling food or water, future implementations, we can put a cover on top of the attachment and seal it so that way, no water or food can get to it. That could be a fix for it. Other than that, I would say don't spill water on circuits. Electrical engineering 101. Johnson almost did that actually before he presented this. It was pretty exciting.
The original griddle comes with like a little collection bucket for like grease, and actually the water spilled in there, so we're all good with it.
Yep.
How do you wash it?
How do you wash the griddle?
You can take the griddle off the attachment.
What about the wires that are connected?
You take them off and you glue them.
Exactly.
Don't ask me about my project.
The glue is cheap.
How does the dartboard detect a dart?
In the text.
Where's the score?
What class is that bottom
That is Advanced Digital Systems with Dr. Hain, day 1,
First day of class.
August 20 something,
23.
23rd.
Can you talk about what was the most difficult part?
Okay, the most difficult part, I'll answer for myself. 100% testing my module, because to my knowledge, I mean, obviously, y'all worked with, sorry. Obviously, y'all got your power from the wall as well, but to my knowledge, we were the only other ones that did and worked with 120 volts. So my module takes in 120 volts and potentially puts 120 volts out too. That presented a lot of issues with testing and safety, and how do I go about that? I mean, Dr. McKinney, you can probably attest to the horrendous testing setup you witnessed one time in 313, and how much of a travesty that was.
No safety brief.
We still have not attended your safety brief.
Did you ever shock yourself?
No, sir.
I would say that's another thing that we had to deal with whenever we were testing, is remembering to turn it off before touching it. Sometimes, he was pretty good, he never touched it, but he was just like in the middle of it. Same thing with the hot surface.
I haven't graduated yet.
Hey! I would say the hardest part for me was originally in the beginning of the year, first semester, was really trying to figure out how to go about designing a new coil without really trying to get over into mechanical, but then I ended up doing that anyway, so then that's why that got discarded. And then once that part happened, it was just more of trying to figure out how to safely make all the connections, because I was in charge of the power supply, and making sure things were connected where they should be. That's about that.
I would say one of the hardest parts of my module was figuring out how to input a new temperature value after one has already been inputted. You need an interrupt for that, because the way our code works is it's in a loop. In order to start the loop, you need to input a number, and it goes into his loop, which is a while loop. So it will just keep running through his loop. And so what we did was we implemented an interrupt button called clear, and that takes his loop, which has a flag set to 1, and mine, which is a flag set to 0. You press it, sets the flag to 0, goes back to the start of the loop. It's where you can input a new value. It's an accepted value, it starts his loop over again. But that was very painful to find out and do.
Yeah, my hardest part is probably like figure out how to separate the wire, not to touching the metal part and the coating. Thank you.